Hello, and welcome to PreCalc. Wow, don't even know what class it is. PreCalc Lesson 119. You guys are almost there. You have 6 lessons left. Now, this is probably, if you thought PreCalc was hard at any point this year, this is probably the hardest lesson conceptually to grasp your mind around. So, pay close attention, ask tons of questions. Today, we're learning Descartes' rule of signs. Not S-I-N-E-S. Okay, maybe it's not the hardest lesson, but it is like a conceptual thing where you have to think through it. So Descartes' rule of signs says this. He's French, so that's why they spelled his name weird. This goes back to graphing polynomial functions. So we've been graphing them. We did the rational roots theorem. Then we tested to see which ones were roots by using synthetic division, plugging in the numbers, and seeing if the remainder was 0. But now, this guy, he decided, well, I'm going to figure out more patterns. And I'm going to look into this further and see, is there more information that I can glean from a polynomial? So, let's suppose we have this polynomial here. Descartes' rule of signs tells us this. And it really has to do with the signs, so that's plus or minus signs in front of each term. So in this one, we have a plus, we have a minus, and then we have a minus. So Descartes' rule of signs says the number of positive real roots, so that means you're going to have a positive number, and that's the root, of a polynomial equation with real coefficients, so that means we don't have any imaginary numbers, equals the number of sign changes in the polynomial p of x. So here's our polynomial, and what Descartes says, or what his rule of sign says, is that the number of times the sign changes in front of your terms gives you how many positive real roots there are. So this changed once. So there is one positive real root of this equation. Okay, I'll write that out. So we have the number of sign changes equals the number of positive real roots. So again, this doesn't guarantee rational roots, which is what we were talking about earlier with the fractions. This is, you're just going to have roots that are positive numbers and not imaginary. That's it. Now, what about the negative real roots? Well, for that, you actually have to find p of negative x. So you're going to have to plug in negative x to your polynomial. And what that's going to do is it's going to change some of the signs. So if I plug in negative x to x squared, well, let's just show our work here. This gets transformed. A negative squared changes nothing. So this is still positive x squared. But now I have negative negative, which is plus x minus 6. So here I see that the sign on the x changed. Now I have positive, positive, and negative. So between these two, there's no sign change, right? Because they're both positive. But here, it goes from positive to negative. So that indicates that there is one negative real root. So the negative ones are a little bit more tricky. It's number of sign changes in p of negative x. So again, you're plugging in negative x for x, and then you're doing the same thing you do with the positive ones. So the number of sign changes in p of negative x is the number of negative real roots. So one of these problems could say, how many positive real roots and how many negative real roots are there of this equation? Okay? And you would use Descartes' rule of signs to find it. Are we surprised if I actually just factored this one? Just off to the side here. This is x minus 3, x plus 2. So you know that you get one positive and one negative. So we're not surprised. Let's pick up something a little bit more complicated. Now you might ask, what if there's powers missing? You just ignore those. You're still just doing, as long as they're in descending order, so you have the highest power first, and then you go down. If you're missing like the x term, that's fine. You're still counting the number of sign changes. So we have x to the fourth minus 2x cubed plus 3x squared plus 4x minus 7. So first of all, I'm going to start with the positive one where I just do the x's normally. So I have plus, minus, plus, plus, minus. So how many sign changes is that? Well, this one goes from plus to minus, and minus to plus. And then this is not a sign change because it's both positive, but then this one goes from plus to minus. So this tells me that I have 3 positive real roots. So if I'm solving this problem, I'm looking for 3 positive numbers that will make it 0. Now, I'm going to plug in negative x for x to find the negative roots. So I have negative x to the fourth minus 2 times negative x cubed. Remember, a negative to an even power is just going to go away. To an odd power, it will change. Plus 3 negative x squared plus 4 times negative x minus 7. I've tried to line those up as much as possible so that you can see what I'm doing here. So negative x to the fourth is simply x to the fourth. This one is going to be negative because to a cubed power, I get that negative out. So this will end up being positive 2x cubed. This one will not change because it's to an even power. This one will change because it's to the first power. So let's look at our signs. The numbers are the positives and negatives in front. So in this case, we have positive to positive, so that's not a change. Positive to positive, not a change. Positive to negative, so there's one change there. And then negative to negative, that's not a change. So it looks like here we have one negative real root. So then from there, if I actually had to find these, then I could go in and do the rational roots theorem, start dividing, and go from there. All right, let's skip that next example and go from here. So with that said, this is another tool in your toolbox to be able to find the roots. Now, this is where the pre-calc lessons draw out and get longer and more painful as they go on. So I apologize, but I'm glad that we get to go at a decent pace. So with that said, now we're going to talk about what happens when you find a root. And specifically, should you keep looking for roots? This is really important because up to this point, and you can think in early mathematics before they had calculators, before they had graphing calculators, they're doing all of this by hand. And so you want to know when you're done looking for roots. And so if you say, well, there's only 3 positive real roots, and you find them all, you know you start looking at negative numbers. You don't need to keep plugging in positive numbers from your rational roots theorem. But we also want to know, and this is called the upper and lower bound theorem. We want to know if we've gotten the highest positive real root or the lowest negative real root instead of keeping going. Remember how we talked about the region of interest and we're just plugging in random numbers? We did the rational roots theorem where you're plugging in random numbers. You want to know when you're done so that you can go the other way. Okay? And so the idea is this. Let's suppose we have a function that looks like this. That's a classic x to the fourth, right? And it looks like it is x to the fourth minus 13x squared plus 35. Oh, I missed something. So let's go back over here. Descartes' rule of signs isn't as straightforward as I presented it. So, although this pointed us to saying that there are 3 positive real roots, unfortunately, there might only be 1 positive real root. And why is that? Because roots will come in pairs most often. And so, you could have 3 or you could have 1. Because you can lose 2 at a time. And so let's say you got 7 positive real roots. And Descartes' rule of signs said you have 7. You could have 7, or if 2 of those just so happen to be imaginary, you would have 5. Or if 2 more of those are imaginary, you would have 3. If 2 more of those were imaginary, you have 1. Okay? And so you really, it gives you an idea of what kind of solutions you're going to get, but unfortunately, it could be any of those options. So for this one where we found 3 positive real roots, it could be 3 or it could be 1. Now, here's what's great. If you find that you have 1 negative real root, you have 1 negative real root. This is like guaranteed. But if you have a number higher than 2, and I believe it includes 2, includes 2. Yeah. So if you have like 2 real roots, then it could be 2 or it could be 0. And so that's the bummer with this. It's not as cut and dry as I presented it. So whatever number you get, if you can subtract 2, that's also an option. If you can subtract 2 from that, that's also an option. If you can subtract 2 from that, that's also an option. So, yeah, it gives us a guide. It gives us a direction to go, but we're not always guaranteed. So, let's look at this guy here. So we see with Descartes' rule of signs, for this, x to the fourth, that we would expect, let's look at the signs. We have a plus, a minus, and a plus, so we would get 2 or 0, right? Because you can subtract 2, so there's either 2 positive or 0 positive. I've already graphed it for you, so you can tell that there's 2 positive real roots. And then I'm going to plug in negative x. Let's see what happens. So I have plus to the fourth minus 13 squared plus 5. Since these are all even powers, nothing's going to change. Right? These negatives go away, and I'm left with x to the fourth minus 13x squared plus 35. So we have a plus minus plus again. So I have 2 or 0 negative real roots. In this case, I have 2. The only way you're going to know is if you start plugging in points. Sorry. So, now the question is, how do I know that I've gotten the highest one? How do I know if I've gotten the largest value? So I will stop looking in that direction. If you look at this, you'll notice that the region of interest is quite large, right? 36. I don't want to go until I hit 36 and try every single number. I want to know when I'm done, when I've hit the highest number so I can start looking elsewhere. And so the way we're going to do this is as follows. The book says to determine an upper bound for the real roots of a polynomial equation, so that means once I've hit the highest number, we use synthetic division and use positive integers as divisors. If every non-zero number in the bottom row is positive, or if every non-zero number in the bottom row is negative, there's no real root greater than that integer. So, right now, my region of interest is 36, because I took the highest number and added 1. That's massive. And so, let's say I want to slim it down and see Well, will 10 be a good upper bound? So what I'm going to do is I'm going to do synthetic division. And remember, the power of synthetic division is it gives you a polynomial afterwards. So I'm going to bring down this number. 1 times 10 is 10. 10 times 10 is 100. That's 87. 10 times 87 is 870. 10 times 870 is 8,700. That's 8735. So if I write out the x values, this is so fun and plural. You'll notice that all of these are positive. Since they are all positive, there are no sign change, then I can reduce my upper bound down to 10. So I'm going to say, oh, here's 10. I'm not going to look any further because I know that nothing interesting is going to happen. Again, go back to when people were doing this by hand and they were manually plugging in these numbers to solve their complicated physics and math problems. You would want to narrow that down. Okay? Now, the same goes for the lower bound. We're going to use synthetic division and we're going to plug in a negative sign here. But for a lower bound, let's just read it. We use synthetic division, we use negative numbers as divisors. For lower bounds, we look for alternating signs because a bottom row of alternating signs tell us that the divisor is lower and there are no real roots less than this number. So here, we want them all to be positive, and that says there's nothing to the right of that. But for our lower bound, we want all of them to be alternating because we want all of our roots to be above this. So for the upper bound, just to reiterate, you want all the signs the same. But for the lower bound, you need all of the signs alternating. So you need a plus, plus, minus, plus, minus, plus, minus, or minus, plus, minus, plus, minus, plus. So let's try a lower bound of negative 10 and do the same thing. 1, 0, negative 13, 0, 35. We'll zoom in a little bit so you can actually see what I'm writing. Okay. So bring down the first number, you get 1 by rolling card. Negative 1 times 10 is negative 10, so this is negative 10. Now if you multiply these, you get 100, so that would be 83. Multiply negative 10 times 83, you get negative 830. Multiply negative 10 times negative 830, you get 8,300 plus 35 is 8,335. So what do we see here? Well, I have a plus, minus, plus, minus, plus. They are all alternating, and so that allows me to say that negative 10 is a new lower bound. Woo! So let's recap. Descartes' law of signs says the following. The number of sign changes in your original polynomial gives you the number of possible real roots. Remember that if that number is 2 or greater, it might be wrong. It might be 2 less than that, it might be 4 less than that, and so on. All the way down to 1. Okay? You'll never get a negative number of roots. Okay? Then you plug in negative x, and that will give you the number of sign changes there, will give you the number of negative real roots. Again, it could be that number, or it could be 2 less, or 2 less, or 2 less than that. Okay? Now, we talked about that, then we went to the upper and lower bound theorem. The upper bound, we want no more zeros to the right of this, so you want all of your items, or all of your terms, to have the same sign. That tells you that there's no zeros past whatever number you try. For the lower bound, we want all of our zeros to be to the right, so we need every sign to change. Okay? How do we figure that out? Well, We plug in a number, and then we check and see if every single sign is different, then we're good to go. And that is the very painful, very mind-heavy problem set 119. Great job.